Which one do you want to start with?
Are you working off that one, or you have them all open?
This is.
Did we do that one already?
This doesn't look too difficult.
Is that? Oh, it's a problem. I think you just put that into phaser form, right? You did that one.
We've also done this before.
You might have, yeah. I think you just use analysis or something on it. And he did that one class for sure. Yeah, he did this. He definitely did that one. So probably should go through that one.
Okay.
I have a big problem with Fourier. Like, I don't understand Fourier series.
So Fourier series. So when you have any signal, you can break it down into subsignals of sine waves, and when you sum those up, it gives you that signal.
So isn't it
original signal?
Is it called superposition?
So
you add up those.
Yes.
Yeah.
So sine waves are our favorites because it doesn't have harmonics. A perfect sine wave will not have harmonics, so it won't affect other circuits. Well, that's pretty much it.
Just do examples.
Yeah. Do you have any particular problems in mind, Peter?
I'm gonna have to look. I know I definitely have to review the three-phase stuff and like the transformer stuff. Those are the main things for me.
So make sure when you're reviewing, create the cheat sheet once. A longer one, don't worry about space. Then create it again. Make sure all the formulas are correct. Because if you have something wrong with the formula sheet, it's gonna mess you up. And I think that has happened to someone in midterm 2.
That happened to me in the first.
That happened to me in the first as well.
I'm feeling pretty good about ones like this, finding the power and stuff.
Like that one?
Yeah, like that one.
Yeah, that one's okay. So it's not the worst.
And the Laplace one doesn't look too bad either.
Yeah, as long as we get to use the sheet, it's just going to end up the way it always does. You're going to have to use some partial fraction and then turn it back.
I'm thinking he's going to ask something about transformers though, because he specifically went over that one in class.
He did pick that up himself.
Yeah.
We didn't do that.
For me, it's been very, very difficult to predict what comes in Professor Shanichi's exams.
I've been pretty accurate. He always picks one that shows up on every single one. That's a question. It usually is. So this one so far, I saw that they all had a mode question, I think. So that one's going to definitely be there. Doesn't it? Or does this one have one? Most of them have a pattern or something.
Shabarno, what's up with the dots on the transformers? Like with the way they're laid out? Because I tried following like the diagrams and stuff, saying if they both enter, if they both leave, it should do this or that. And sometimes it doesn't seem to match up exactly. I'm not sure. Let me try.
The book was messed up or something because I saw that as well. Once I ignored that, everything was fine. Just that one note, it was there a set of 4 of them or so.
Yeah.
And it did, whatever happens, but one
I think
was incorrect. One was incorrect or something.
Yeah.
Because that one didn't. Yeah. One of those 4 was incorrect.
It was really weird.
But otherwise, it was fine. I can't remember which one it was. It was one of those that didn't match up with the way it's supposed to.
Well, with the dots, when you have a voltage across this inductor or the primary turns over here, if you have a plus here, that plus shows up over here. So the voltage flips if you have the dots on the opposite sides, and it's the same.
What if the voltage, what if it's V1 and V2, but both the pluses are up top, but the dots are like that? Because, like, I don't know. Because, like, that's how it is in here, at least. Like, these dots are, might be flipped. Like, the plus and minus are always on the same side. Really, all of them. Is that, I don't know if understanding what you're saying correctly. But
No, this is fine. when the dots are on opposite sides, right? But you have V1, the pluses on the same side, right?
Yeah.
So one will be the negative of the other times turns ratio. And that's what you had here. For D, the dots are flip-flop, right? And the pluses are on the same side, minuses on the same side. So V1 over V2 is negative of N1 over N2.
Oh, they're opposite.
Yeah. But if it was this plus you place over here, it would be the same.
Okay.
Same symbol. This is just convention. In the exam, you'll get to choose what to put, unless he specifies that this is V1, this is V2, and find V1, V2. And if he doesn't do that, you're doing, say, nodal analysis. You put the voltage, so you get to decide what's what.
Oh, okay. So you can say like minus.
So, what's that to mean? Negative. So which one do you want to solve? Did he solve this one?
He solved this one, but he said that there are several ways of solving it.
What did he do?
He
So
he
he
used
did
source
source
transformation.
transformation. He said you could use, I think, mesh. Is it mesh?
Yeah, I think you could use mesh.
Oh
You can also move everything from the left to the right.
yeah. He said move the right to the left. Yeah. But I think he did left to right after breaking that one down a little bit.
So
What
here,
what do you think the easiest way to go about it is for him? Do you think it's to flip it over to the left, or?
I would, if we use source transformation. Oh, if you choose to move everything to the left, you have to remember to change it back. You won't get the right answer for ZL. You'll have a multiple of ZL, so you have to change it back. What I would do is, if you use source transformation, it makes it really easy. You source transform here, you have something in parallel with this one. Then you find the equivalent over there. You can do source transformation again. There will be a resistor in series with this one. You can source transform again and find the equivalent resistor. Then you can move them all to the right. Is that what he did?
Yeah,
that's what he did.
Okay. If you want to do mesh analysis, we can try mesh analysis. Let's try it. Oh. Okay. So we have three meshes here. Let's assign voltages. Is the color weird? Is it like
It might just be right.
I'm using red? That doesn't look red. That looks much better. Okay, I don't know how to fix it. So the V1 to that. We'll have three meshes. Two. Let's try to write down the equations. Starting with mesh 1. I1 times 1 J2 I1 plus V1 plus 1 times 0. This is K1. Next 2 minus 40 0 plus 1 times I2 I1 0. Minus V2 J1 minus J1 I3 plus I3 0. Let me double check the question. For this one, actually, what we can do, the other thing we could do is, did you do find the Thevenin equivalent? That's the best method. Okay, this is how we can do it too. So first we open circuit this. We'll call it V open circuit. So I3 is actually 0. We'll get to that later. So we have here 1, 2, 3, 4, 5, 6 unknowns. We also know that since that's open circuit, I3 0, 4. V2 is twice in what? Not in the other direction. That. Usually one more equation. Be probably on the current ratio, I3 equals this is also going to be negative. -1. You see the book again? So 6 equations. 6 unknowns. You have to solve them to find VOC. That's the first step. You guys want to try it? Shouldn't be that difficult. You can plug in I3 here. This comes out to be 0.
V2 is equal to 3 open circuit.
Yep.
V2 is equal to 2 times.
So all you have to do is find V1. This current is also going to be 0. I1 is going to be 0. You plug that in here. V1 comes out to be 0.
Wait, I1 is equal to 0?
Yeah, since this is open circuit, which means infinite resistance, you push it down here. Here's an infinite resistance over here. So there's no current through here. By this relation as well. Since I3 cannot flow over there, open circuit, and this relation exists, I1 is also going to be 0. So you get also V1 equals 0 from here. No, V1 equals to minus I2, or I2 from here. So V1 to be 0. This is 0. So V1 equals to I2. And this one's 0. This one's 0.
I2 is equal to 40.
I2 is 40, so V1 is 40. V2 would be negative 2 times 40, so minus 80. Make sense? Try it and see if that's what comes out to be.
What was the answer?
I have negative 80 volts as VOC.
You're trying to find the max power.
Yeah, that's not the final answer.
We're going to have to find that short circuit.
Yep. Next to a short circuit is
Do you think it's best to use Thevenin's equivalent to solve for max power all the time?
since once you find ZTH, that's always going to be the conjugate of CL.
Yeah.
Yeah. The other way to do it is to find a function for power transfer. Then you find the gradient, or dV over dt equals 0, or dV over dz equals 0. And for that, you find Z. The mesh again. Equations for I1 and I2 will remain the same. Is there any changes there? Carry over these two equations. This one. That one. For I3,
So the equations remain the same.
Except this one.
So you have 1, 2, 3 equations, 4, 5, maybe one more. Take super mesh. Here. Equation. It's going to be that'll be your 6th equation. And 6th equation, 6 unknowns, you can find them all. Does that make sense? Any equation you don't see? Or anything you... I was feeling very confused. Any part you want me to go over again?
So once you find Z Thevenin, then what's the equation for max power? Is it, because right here it says V Thevenin over 8 over R Thevenin, but I'm not sure. I'm looking in a different, I'm looking in chapter 11, but it still should be the same, right? Because
What does it say?
It says, well, the max average power transfer is going to be equal to the complex conjugate of that. But what about just, was he asking for the max average or just the max power?
I think he's asking for both. Impedance ZL, such as it would absorb maximum power and maximum power. Once you have I short circuit.
I think he did average.
By finding ZL, no. By finding Z Thevenin, ZL is the conjugate. That's it. And that's your maximum. That's the impedance that would absorb maximum power.
Yep.
Oh. And then you just find the power.
He used RI squared, which is the normal original.
Oh, that's right.
So he used just average power for his answer yesterday. But I don't know.
Yeah, I don't know which equation.
I mean, I guess if you have if you have ZL, you already have the maximum it can go. So
Yeah.
then by using that impedance and doing
Just
RI
normal
squared, you
stuff,
get
yeah.
the maximum.
Just use the R. I guess it's a complex. ZL has 8 minus J6. It looks like he dropped off the J part and just used the R part of it.
Oh, well, once you have ZTH, right? And you know that this is going to be ZTH conjugate. And you already know the open circuit, which is VTH. You already know this part. And ZTH will equal to L equals. So this would cancel. Only have the real part left.
Oh, that's why.
That's the maximum power transfer over both of them. When you have to find ZTH or V of ZL, you still have to do the voltage division. Voltage division, and you can do V squared over R, V squared over Z.
He said, find the impedance of ZL such that it would absorb maximum power.
Yep.
And the answer is 8 minus power is squared by. Yeah. Just the real power in the answers.
We just did RI squared.
Okay. Which one is it?
Spring 2012 number 2.
Okay. It's best to ask during the exam what he wants. Where was I? Any other questions regarding this one? The easier way to do it is the one he showed in class.
The short transformation.
I think that was
After you flip it, then that's when you find the Thevenin's equivalent, and then you have to flip it back. You said.
For the way he did it, if you move everything to the right, you don't have to flip anything. If you move everything to the right, ZL, there's no, you haven't changed ZL, transformed it in any way. But if you choose to move ZL to the left, what happens is you have two meshes, right? It becomes really easy to solve. If you don't flip it, switch it back, it's not going to give you the right answer.
So you could, this might be class, but you could use source transformation and then just move everything on the left to the right, and then that would be the correct Thevenin's equivalent.
Yep. And similarly, if you choose to move everything to the left, current will decrease, so you divide by square of the thing, right? So this becomes the same. Minus j over 4. ZL. I actually do find the correct ZL, since the factor of 4 is there. It's not inside ZL. You'll find the correct ZL. But when you do take the open circuit, it's very easy to forget there's the over 4 there, and you find Z, not Z, PH is going to be 4 times, or 1/4 of ZL. This one's easier because you don't have the V1, V2, you have fewer variables. when solving it. When you open circuit this, the current here is 0. That's really, really easy to see. Yeah, you can do that.
So when the ZL is the open circuit, so it's just the bottom one? Just bottom. Just the bottom circuit.
Which one? This one?
Yeah, just the bottom loop. Because the top one will be the open circuit.
Yeah, right. Top one would be 0, so you have to find the voltage across this resistor. Because there's no voltage drop across anything, any of the elements. So the voltage drop that's here, that's going to be the voltage drop over the open circuit. If you just find the current here, these are also all resistors. Oh no, we have a capacitor there. You find the current there, and current times voltage, you find the voltage. When you short circuit it is still easy.
And if you say like you did the source transformation on the left side and you're gonna flip it on the right side, but the dots are on the same side, does that change? It changes. Like how do you transform it if the dots are on the same side?
If the dots are on the same side, the voltage you get, the voltage source, you don't do anything to it. You take that voltage source over. Since this is flipped, you'll have to put a minus on the voltage. Okay. Once you flip it to the other side. Or the current. It will be the opposite. So what do you want to do next? This one's doing the other way. It's very long for 25 points. For the IS RMS value, do you just square these and take the square root? Square of the magnitude or coefficients. Zero of t, that's current division. Average power. Which resistor? This one. Oh, there's only one. That's I square R.
Seems too easy.
For this one, I think what you have to do is think of the current source as superposition. Three current sources. They'll be parallel. This is what it will look like.
You did this one also.
Did it? Is this how you did it? I don't
He didn't
think
explicitly write that down, but he did add them all up. He didn't write that down, but he added them all up at the end.
This is the way I would do it. This is J omega.
You did it one by one. Like
DC and because they have different frequencies.
Yeah, so for different frequencies, this would be J. The omega is different for different ones. For example, for the 12 amps, this is 12, it's 0, so these don't do anything. This would be a short circuit, that would be an open circuit. For 4T, so you do each of them one by one, then you add them together.
Wait, are you doing short and open as in it's going in steady state? Like, like it's a DC circuit, but it's steady state, right?
Yeah, because once you consider the 12 amps, this one is DC.
Okay.
And omega will be 0, so
Yeah,
that
so
gets
that's
covered.
0.
That becomes a thing.
So all the current is going through that one. You won't have a voltage here or current there. I of 0 would be 0 in that case. Then you add them together to get I of t. How do you find the average power though? Do you take them separately and that's up to you?
Yeah, you take the current out of the total current after you got it.
I of 0?
Yes.
I0 of t square times r.
I feel like that's too
That's
simple.
25 points.
Unless,
Oh, okay.
unless his man wasn't
Is that what he did? Did he do it?
what, simple, what the way he just did.
I can't remember.
Was
Did
his
he do,
math the same one?
yeah, did he do I squared R? Or C?
Um, yeah. Over 2. Okay, so he assumed it wasn't RMS. So it's over 2 for his average power. I said he assumed it wasn't RMS. He did ask us for RMS, so I guess he's assuming that the original is in the other one. Was it M? Was it maximum? What do you call it? So when he did his power, he did R I squared, but he got the 2 from RMS. Or from not changing to RMS.
But what is I?
What is it? How do you do it? So you have
So for sine waves or cosine waves, that's I of RMS or V of RMS.
and you converted the, yeah, that. Yeah, that's exactly what it is.
But how would you find
So he
IMAX.
wanted, it's assumed that that is IMAX. Because
once
it's
you
in-
find say IO of t, that comes out to be x cosine of theta. Something like this. This would be IO max.
Right.
So you can use that as well. But what if IO of t comes out to be multiple frequencies? And you do the IO RMS, you have to find it. By squaring the coefficients and taking the square root. And then you can do I square times R.
So if you do it with the three-way that like you did second ago, we have to change the capacity change.
Yeah, each time. For each one, the inductance and resistance will change according to omega.
What if the problem was not like 12 plus 8 cosine 4t plus 10 sine 8t? I forgot how to change sine to cosine. Was it minus 90?
Yeah, plus or minus 90.
And if you want it, so you want it to be in cosine.
If it's all sine, that's fine too.
Okay, then the answer will just be in sine. It's okay.
Anything else on this one? Which one? What do you guys want to do next? You guys do this one? If you convert everything to phasor, doesn't it become really?
It seems like it.
Yeah, looks like that.
Omega is 1. You have, let's see, change I have 0 of t into phasor. What happens to this? So J omega L and so on. You do mesh analysis, 3 meshes. You'll have a constraint equation over here. This is a current source. You can do a super mesh around this one. So you have 3 equations, 3 unknowns. Where's V? Oh, this is VO. So you also have VO in terms of, say, I1 and I2. I1 over here and I2 over here. So that's not a problem. I don't see any more complexity than this. Do you guys see anything? Any trickiness?
Seems pretty straightforward.
Doesn't normal. It looks pretty straightforward. The only constraint equation, if you use mesh, would be that current source, right? Like nothing with the voltage sources.
No.
Yeah, it doesn't look too bad.
Can we do it though? Can you?
Okay. Try to copy this. Dude.
Smart board's not so smart after all. How do you like working with the smart boards, Barno?
Not really.
Yeah, it was kind of a pain.
Whiteboard is much easier to use, but you can't record the whiteboard.
Oh, yeah.
To okay. Let's put it in phasor form.
Which test is this?
Unit 12.
Spring 12?
Just call this I don't know. Constant integration. do mesh 0. Start on the middle. Simplify this. Does I1 come out to be 0? Did I miss something? Oh, there's 2 here. BO equals I2 minus I1 minus IO times 1. That's 2 equations. You need one more. So we can do super mesh. Or we can take this mesh. This gives us J I1 minus 2 I0 plus I0 minus J I2 with everything. That's 3 equations and 3 unknowns. That's what helps. You guys want to try to solve it? You can just plug it in to calculate and to solve it for you. Except the J's. You probably try to solve it in Google Chrome. Once you find I1, I2, and I3, you can find BO, you can find IO of T. Remember to bring back the cosine. This. And when you have to find average, just the magnitude, or we'll have I max, which is the coefficient of the cosine, and that squared over 2 gives you the GRMS squared, and that times the R, which is the average and R is 1. So something to be careful about this one for VO. There's two currents. This is going to be, if you take this as clockwise, it's going to be I1 is I0. I1 minus I0 is the current going through. Nothing tricky here. So this is out of 75. Where's question 4? That's weird. Yeah. Okay. So that one's done. We have 9 more minutes. You guys want to try to do one? Which one? This one is again ZL. This one seems easy enough. Where? Which one?
I'm not sure which one.
I'll say like spring 2010 or something. Or I swear it's the last question. I'm pretty sure. I just drew the circuit.
I didn't copy this stuff.
Let's see a Fourier series question other than the one that the professor solved in class. That was a Fourier series one. Oh, this could be, yeah. So it's considering only the first 2 terms of the series.
Wait, did he do this one in class? He did this one in class. These two.
I think the sample papers are easy enough that he'll finish it. He might be able to finish in class, other than these ones. These ones usually take longer. So you have to find material for me to go over 2 hours of on Friday.
Try to find some examples or something.
Still quite a few problems.
Yeah. Most of them are similar to each other though. Like there's a lot of average power ones.
So for Fourier series, so if you missed it, any signal can be broken down into sum of sine waves. That's the basis of the Fourier series. And each successive term would have a multiple of the main harmonic, or what's it called, fundamental frequency. And each successive one would be some multiple, n omega. And once you add them all together, you get the primary wave. I'm currently going over that in power electronics. That's ECE 411. Sometimes you might want to eliminate higher harmonics because they waste power.
Yeah, isn't it like kind of instead of giving something like if you want like 60% of the voltage, instead of giving it 60% of the voltage, for AC is just kind of like keeping it on 60% of the time. Is that the same concept?
Similar, yeah.
Yeah, that's right. And then that reduces how much power is being wasted, kind of. Yeah, that's what I thought.
You, did you want to do a power one? I don't know if we have enough time.
We have 4 minutes. Which power one?
Problem 2 in spring 2010.
See this one? Let's look at it. An industrial load consists of balanced three-phase Y-connected load with a phase impedance of that in parallel with a balanced three-phase of delta-connected load. Okay. Phase impedance of Y-connected load that is equivalent of the industrial load. First thing you can do is draw the circuit because it gives you both connections. You can do the Y. Box. We have 8 minus 4 I J. All of them. And here it's 6 plus 12 J. There's a relationship between Y delta, right? One is a third of the other.
Y delta.
When you do impedance.
All for the impedances.
Impedance, yeah.
Yeah, that's what it was.
So Y is a third of the delta. If that's the case, the equivalent of this would be 3 plus 6 transferred into Y. Since they wanted Y, we're transferring into Y. If they wanted delta, you could transfer this one, the left one, into delta. Once you see that, you can see that this one is parallel with that one. This one is parallel with this one. And the third one is parallel with the third one over there. Do you see it? You can actually take single phases out, and this is what it will look like. Each phase is 8 minus 4 J. This is 3 plus 6 J. I'm hoping Y delta is 2 times Y. Z delta is 2 times of ZY. This is going to be connected to the load or the power source. This point and that point. So you have to find the equivalent impedance that just use the parallel formula, product over sum. If you do product over sum, you'll have each impedance, each phase impedance. Gives you the current. take the current phasor as your reference and find the phase voltage, the line voltage at load terminal. Since it gives you the line current, you can find the phase voltage. It's Z times I. You have Z equivalent times I would give you the phase voltage, and line voltage is square root of 3 times that. And also you have the 30 degrees during the conversion. Calculate the complex power that the load is consuming. That's I square Z, you can do that. If you do I square Z, it's also going to be 3 times that because the load is 3 phase. You find the power consumed for each phase. That's going to be Z squared times I, and times 3 is the total consumption. Load power factor, you can do P over S, the real part of the complex power over the magnitude of the complex power, I think, right? For power factor, isn't it P? So S equals P plus JQ. Power factor is P over I think that's it. That's the magnitude of the complex power.
Right. P over S.
P over S. Yeah. To increase the power factor of the line, Y-connected capacitor bank. So unity power factor, you know that you have to make Q equals to 0. So minus Q is going to be the power of the capacitor. And you know the voltage across the capacitor from VLL or V phase that you found over here. You can use that voltage. V square over capacitor's impedance would be equal to the Q. And you find from there you have omega C, you know omega 2 pi times 60. Omega 2 pi times the frequency. And you can find the capacitor from there. So it's also, I think you've done similar problems in midterm 2.
Yep. I just don't remember.
Yeah, these are, if you don't practice them often enough, forget. And you'll see more of these in 319, in the beginning of ECE 319. So if you remember this, it's really easy in the beginning phase. In fact, he actually put a question like this in our first midterm, and I couldn't remember what the capacitor bank does. I can do it. Yeah, practice them and bring more problems for Friday. So then we can spend more time solving than looking for problems.
How many classes have you taken with Shinichi?
I took 211, 213, 319, now I'm taking 419.